Distributed Systems and Security Group at Microsoft Research Redmond. His research interests lie in the areas of systems and network security. He received his PhD in electrical engineering and computer science in 2006 and his master's degree in computer science in 2003, both from UC Berkeley. And he received his master ME in 2000 and BE in 1998 in electronic engineering from Tsinghua University in China. Weidong.
Thank you very much, Dongyan. Thank you very much for inviting me here. It's my first time to Middle West. I really enjoy my visit. And today I'll be talking about automatic signature generation for unknown vulnerabilities. It's a joint work with my colleagues Marcus Peinado and Helen Wang. Carl Chen and Michael Lacasto was involved in this work when they did their internships. So zero-day attacks that exploit unknown vulnerabilities is a big problem because zero-day attack means there is no patch or signature available to detect them or to filter them out. Symantec found there are 20 unknown vulnerabilities exploited between July 2005 and June 2007. So it's a serious problem, and however, current practice in new vulnerability analysis and protection generation is mostly done manually. So we don't have, so the attack is out there, but we need to take a lot of time to manually analyze them. It's really not a good idea. So our goal in this work is to automate the process of protection generation for unknown vulnerabilities. So nowadays, how can we protect a vulnerable application? The common way is this software patch. So we patch the binary of the vulnerable applications. And the other way is use this input filter. You can think about input filter as either like a network firewall or module sits on the I/O path. And a data patch, we call data patch, is basically we patch the input instead of binary. The advantage of data patch comparing with software patch is for software patch it's hard to roll back and takes a lot of time to do, and it's time consuming. For data patch, we can roll out a quick data patch. If things changed or doesn't work very well, we can easily just take away because it's just a filter. So our work is focused on automatic data patch generation. Here, let me give you an example of what we mean about data patch. This is a data format specification. So here, specify the SQL message. The SQL message for the slammer attack is basically have a first byte as a type and followed by a buffer, a sequence of bytes. Then there's a state machine, and state machine for SQL attack is quite simple. This is for the SQL protocol here. And here's a handler. And the data patch is basically a vulnerability predicate on the input fields. Here we can see that the data patch says if the first byte, the type equals to value 4, and the size of the rest of the message is greater than 97, then this is an exploit. So what we are looking for is this vulnerability predicate on the input fields. So to solve this problem, we developed a system called the ShieldGen. The goal of ShieldGen is to automatically generate a data patch for unknown vulnerability, given an attack instance and its format. The basic idea of ShieldGen is the following. So we construct new potential attack instances, we call them probes, based on the initial attack instance and the format. Then we feed this constructed attack instance to a zero-day detector, to an oracle, to decide if this new instance will trigger the attack or not. We do this back and forth so that we can figure out what matters, what doesn't matter in the original attack, which give us the vulnerability predicate on the input fields. So here's a system overview of ShieldGen. ShieldGen has 3 components. The first component is the zero-day attack detector. The system works the following. Assuming the zero-day attack detector monitors suspicious traffic, Then when the zero-day attack detector detects there's a zero-day attack, it will send the zero-day attacker to this data analyzer. Based on the data format, the data analyzer will parse the zero-day attack and to generate the semantics, all the fields, all the sequences of the attack data, and parse it to this probe generator and analyzer. The probe generator and the analyzer will construct new attack instances based on the semantics and the original attack instance to construct the probes. Send it to the zero-day attack detector. The zero-day attack detector will say, oh, this probe successful, means exploit the vulnerability or not. We do this back and forth based on the previous probes until we can generate a data patch. So for the zero-day attack detector, actually anything that can detect attack can be used here. But in the actually, before I talk about zero-day attack detector, let me give you a background on this dynamic data flow analysis. So dynamic data flow analysis, the basic idea is to track the propagation and operation on input data. Assuming here we have the chunk of memory, and we track the syscalls of the input function. For example, like a read file or receive a network message. When we read the input, we'll mark the buffer that stores the input as tainted. We also track the taint propagation, so when the memory is copied to another part of the memory, we mark the destination buffer also as tainted. The dynamic data flow analysis allows us to understand how the input data is being processed. So I want to introduce dynamic data flow analysis because the zero-day attack detector and the following work about the Tupni both used this technique. So in the ShieldGen system, for the zero-day attack detector, we use a system called the Vigilante. Actually, ShieldGen is not limited to use Vigilante. Anything that can be used to detect attack can be used here because it's just an oracle. And some Vigilante use the dynamic data flow analysis. It basically check 3 conditions. For example, it will check if the input is ever being used to overwrite the return address, or the input data is being executed, or the input data used as an important argument to syscalls. So Vigilante also can identify the offsets of the offending byte, which we will use later on for our vulnerability signature generation. The second part of ShieldGen is this data analyzer. What is in ShieldGen? We use GAPA. It's a generic application level protocol analyzer. What GAPA does is GAPA has a generic runtime. Given the protocol spec and given the network traffic, GAPA will parse the network traffic and provide the the protocol context. For example, which protocol state you are currently at, what are the fields in the messages. And also GAPA can be used for file format specification and analysis. So the question is this: GAPA requires all kinds of data analyzer. They require this protocol spec. The question is, what if when we see a zero-day attack and the data format, the format spec is not available or takes a long time to derive? Our solution is to combine ShieldGen with a new system called Tupni. Tupni will replace this data analyzer, and we don't require the data format anymore. We just require the vulnerable program. It's always there. And what Tupni does is Tupni can, based on the vulnerable program, Tupni can parse the zero-day attack and generate attack data with semantics. With ShieldGen and Tupni, we can automate this complete loop. Basically, here shows that once we receive a suspicious traffic, everything is automated, and at the end, we can derive the data patch. So in the following of my talk,